worked in industry, I was an engineer. So very briefly, I just want to give you a little bit of my background. I have a degree in physics, mechanical engineering, and material science. Two of the schools are state schools in New York. And then I am currently the graduate director at RIT for a program, a master's in robotics, in advanced manufacturing, but one of the concentrations is electronics manufacturing. So we graduate master's level students who have done research in the area of electronics manufacturing. I'm an associate professor. Been working at RIT since 2014. Prior to that, I was a manager of a research consortium called the Area Consortium at a company called Universal Instruments. Some of you may be familiar with the company Universal Instruments, pick and place. They did not really let me touch the equipment. I was an analytical guy. I was doing failure analysis. So all the years that from 2000, well, really 2002 to 2012, I worked as a root cause failure analyst for industry, not just customers who owned Universal equipment, anyone. Anyone could contact our advanced laboratory, and we would do I want to use the word forensics, but that's probably too difficult a word. I would analyze the product and try to reverse engineer what went wrong with the manufacturing process or what may have happened to the product when it was in the hands of the customer. So that's really what I am going to be talking about today. It sounds complicated. It is complicated, but like any process, right? It's amazing we have cell phones today. It's amazing we put people into space. If you take any one piece, it's not all that, it's not so difficult. You just have to break it up into pieces that are understandable, and then you can come to a conclusion that is logical. So I'm going to try to explain that to you today as best I can, and at the same time show you lots of cool pictures of terrible, terrible things that I hope will never happen in any of your factories or with any of your materials. So one of the benefits of being in a laboratory like this is people would send me problems that they could not determine themselves. If you're in production, your number one objective is to get the product out of the door, right? So you're going to troubleshoot, you're going to try to solve a manufacturing problem right there, right during the manufacturing process. But if it's unsolvable, if something gets through the manufacturing process and ends up in test or in functional applications not working, it's very hard to go back and make changes. So if they couldn't figure it out, the most difficult ones, or quite frankly, when money was on the table, there was a lawsuit between the producer and the owner of the product, they would contact my laboratory and we would try to explain what happened. And it sounds terrible, but place blame, right? I mean, everybody wants to know what the root cause is, what the problem is. And if we can determine that, even if you're at fault, you know how to solve it. You say, oh, I'm not going to go find a new supplier. I'm still using this company. But now we know to make sure this never happens again. Jorge? Javier, man. Martin, right? Javier. By the end, maybe I'll get it. We'll see. SMTA. I've been a volunteer for the SMTA for a very, very long time. This doesn't even do justice to how long I've been involved with the SMTA, but these are all my appointments. I was a vice president of a chapter in New York back in 2010. That's misspelled, sorry. And it's not right. But I was also the president of that chapter. I got on the SMTA board in 2013 and served for 6 years. Took a year off. And then, like a crazy person, they said, Martin, will you run to be president? And I said, Do you know there's a pandemic that's happening right now? Why the heck would I want to run an organization that does events during a time that no one can leave their house? But I decided to run anyway, and was the president of the SMTA since 2020. So that's my background. One more thing on SMTA. If you are a member, we have this knowledge base where if you have a login, you can type in things like failure analysis. You in the back probably can't read that. And here is 240 results on papers that have been written in the area that contain the words failure analysis. And what's really important about these 240 papers, they're not written by academics that are doing research on fundamental science. These 240 papers are written by industry, by those of you similar to in the audience that are actually building product. So it's extremely applied. So you might be able to find a paper in this list of 240 that has something to do with stencil printing or something that has to do with pick and place. Oh yeah. I'm not on my home network. My ASM equipment is yelling at me. So that's probably going to happen again. But you can go and find specific solutions to problems by using our knowledge base. It's one of the two most sought after reasons to be a member of the SMTA. Number one is this right here, what we're doing, networking and meeting people. Number two is this. We ask our membership, what are the most important things about membership? This is number one. This is number two. Okay? And me being here is also same as the knowledge base. Me sharing my knowledge with you. Yeah, the most recent one was just in 2002 at our SMTAI show. So, okay, today's agenda, considering coming here to Mexico and there may be a small language barrier, all of you are much, much better at English than I am at Spanish, no question of that. But I have one slide on terminology that are failure analysis. My assumption is these slides will be presented or shared at some point as well. So it's also a list that you can go and do your own research on and learn more about. I'm not going to spend a lot of time on that. I want to talk about defects and break up defects in terms of whether they're happening in production or if they're happening out in the field. Classifications of defects, very simple classifications. There's probably 1,000 different classifications, but I want to make this understandable, and we'll talk about some really simple ones. Identification techniques, how do you identify a failure? That's the easiest thing you can do, right? If I were to drop this glass on this cup on the floor and it breaks, I point at it and I say it's broken. That's easy. It's easy to say something's broken or even be able to say, oh, the glass shattered. What's difficult is to say, why did it shatter? What caused that to shatter? So identification is easy, and we'll talk about non-destructive and destructive methodologies, methods to do identification. What's difficult is evaluation. How do we evaluate the failure and determine why, right? Why is it? And then maybe once you know why, what can you do to make sure it never happens again? So we'll talk a little bit about that. And I promised some pictures of some additional examples of failures that I can show you. Things that are probably very, very, very hard to actually identify and to evaluate. But I want to give you an idea of some of the crazy things that can happen in electronics manufacturing and things that I've seen, some of the more unusual ones, not to scare you, but to say it is possible to be able to figure it out. Who in this room has any experience with failure analysis? I promise I won't call on you. Okay, 1, 2, I just want to know how many, 3, 4, 5, 6, 7. Oh, wow, awesome. Good. I mean, close to half. It's fantastic. So you make sure whatever I say is accurate, okay? If I say something you don't agree with, you raise your hand and say, Doctor, right. Doctor. Okay, so that's good. I'm a professor. I like questions. I like interaction. So I don't have to just stand up here and speak the whole time. If you have a question and I feel really compelled to ask it, please do. And we have people to help translate. So if you'd rather ask the question in Spanish, that's fine too. Okay? Too fast? Too slow? Good. All right, good. Terminology. I could not, we were sitting outside here and I was asking some people, what's the translation of field return? And it's not recall. Recall is something much more severe. So field return, the way I define it, right, is anything that left your factory and comes back, right? It depends on its life, you know. Did it go to another factory that had to be put into another step in the assembly process? If that fails there through some electrical test, it comes back into your factory, I consider that a field return, right? If it gets further, goes out even further, and then gets into the hands of the customer uses it, it breaks. Oh, I'm going to repeat myself. I can already feel it. It breaks and it's under warranty. I have a cell phone, right? If you buy a cell phone new from the factory and it breaks within 2 weeks, what do? You return it. You go back to the store and say it's broken. No money out of my pocket, and they give me a new one. What happens to that phone? Where does it go? If you're lucky, right? If you're lucky, it goes back to the manufacturer. If it's the military, they burn it, right? It never comes back again. But if you're lucky, it comes back to the manufacturer. It goes back to someone who will hopefully do failure analysis, okay? So that's why it's on there next. We have to find wherever it comes back from, whether it's the end of the line, and it's not field return. Field return goes out of your factory. It gets past all your quality inspections, unfortunately, right? Hopefully your quality inspections will catch these things, but if it gets through, not everything's perfect, then it comes back, you have to do failure analysis. So it's not so bad that it's a recall. The reason I say it's not the word recall is because recall is a corporate terminology. Recall means that we issue a press release that says Toyotas need to come back to the dealership because the brakes don't work. And then everybody in the whole world knows, and I, as a consumer, say I'm never buying a Toyota again, right? So that's a recall, in my opinion. Like it's general knowledge. It gets notified to the general public. Physics of failure, excuse me. You can type physics of failure in the knowledge base. You'll get lots of hits. Physics of failure is a terminology. I think it was invented by professors because they wanted to sound smart, right? But it's really understanding more. I like the term mechanics of failure or the chemistry of failure, right? How does this failure occur? What's the mechanism? And if we know the mechanism, then we can put solutions in place. A simple one is conformal coating. If you have electromigration, something's growing on the surface, electromigration is the physics of failure. The solution, potentially, is to conformally coat your product to protect it from the environment. But physics of failure can be applied to failure analysis for any type of failure mode. So you have a failure, I point at it, it's broken. I have to understand how did it break so that I can then put protections in place to avoid it. And I'll show you a whole bunch of examples of that. Root cause, good luck. Root cause is the holy grail, right? We do all this other stuff, and we've actually determined exactly what the problem was. And there's an English saying, I'm going to use a phrase, as the smoking gun. Does anybody know that? Or the silver bullet. Right? And a lot of my customers would say to me, give me the one thing I need to do to eliminate this failure. What's the one thing I did wrong? And very often it's more than one thing. You may be running on the edge of a working process, a manufacturing process, and only one thing has to change ever so slightly. The humidity in the room has to change. And then everything goes to hell and it all starts to fail. But if you change one or two different things, then your process becomes more robust. So I could tell you change one thing, but I don't know if that one thing will solve your problem forever. It may just delay the problem to a later date. Make sense? Analytical techniques, it's not really terminology. It's just a fancy way of saying what tools are we going to use. Some of them are very complicated, EBSD or whatever it is, right? Different analytical techniques to collect data. We want to collect as much information as we can to determine physics of failure, to understand and do the failure analysis, to drive towards root cause. You will not determine root cause without necessarily doing certain analytical techniques, especially if the problem is challenging. Design for, whoops, wrong button, sorry. Design for manufacturability, design for reliability. I have it here, it's in my abstract if you read it for the speech today. The reason I have it here is, what do you do with this information? Once you have the root cause, what do you do? Right? Unfortunately, sometimes I'm going to assume everyone in here is somewhat related to manufacturing. You may not have any responsibility for the design of your product. It may be coming from some engineering group somewhere else that's doing the design. Some problems could not be solved without changing the design. The root cause of the problem inherently is because they made the board 40 layers, right? I'm exaggerating. I've seen a 38-layer board. How many layers? More than 38? No, okay. I've seen some crazy military space applications. One circuit board, this was 15 years ago, was over $100,000. Just the board, no components on it, right? So why did you do that? Right? It's because they have a 10,000 IO BGA on it or something like that. They need all those layers. But the root cause is because there's so many layers. It's something that is nearly impossible to manufacture. Okay? So that's design for manufacturability. Design for reliability goes back to field return. Sometimes you have to change the design in order for field returns not to occur. So they go out and they survive as long as they require to. But then I did root cause failure analysis of things that may have been out in the field for 10 years, but were expected to be out for 20. And it wasn't because it wasn't manufactured correctly. It's because it was never designed to survive 20 years. Destructive analysis, we already kind of mentioned that. We'll talk a lot about that. How do you break things and look at them? And non-destructive analysis, I'm going to assume most of you here in the room are more interested in non-destructive analysis. Why non-destructive? Because potentially you can still send the product to the customer. It's not working, but we do some touch-ups, some rework, and then you can repair the board and still send it to the customer. So that's non-destructive. And I'll talk about some examples of non-destructive analysis. If those tools don't work, then someone has to make a decision that 1 or 2 or 3 boards, assemblies, have to be destroyed to save the rest of the population, right? Can we give up 1 or 2 to be able to ship 1,000 other circuit boards? So that's why you would do destructive analysis, and that's it's obvious the difference between, in terms of the words, the translation or the definition of the word. But why do one versus the other? That's what I'm trying to get at, okay? Failure timeline. I stole a picture here. There's a citation. we have to first determine, one of the first things we have to decide, one of the first things that I would discuss with a customer when I got on the phone with them to do a failure analysis is explain to me exactly when this happened. What day? What hour? What month? Why would I want to know what hour that this failure occurred? Shift. Yeah, second shift, third shift. Someone's tired. What's that? Oh, thunderstorms. Yeah, right. Thunderstorms. Exactly. Yeah. That's also why you might ask time of year. Everybody's telling me, oh, weather's great. It's usually 110 degrees outside, right? And it's dry. We live in a desert here. So time of year could have a very big impact as to electrostatic discharge, right? ESD. I rub my feet on the floor and I zap you with my finger, right? That happens more often when the air is dry than when the air is humid. So there's reasons why I would ask what time of year. So it's important to understand lots of details. The very first thing I do is ask lots and lots of questions. So, this is going to annoy me. I should have VPN'd. It wouldn't have happened. Okay, so failure timeline. And I'm going to zip through this a little bit. Is your failure happening in production? If it's happening in production, then there could be a build quality issue. Looking at your IPC standards, you're probably familiar with IPC A610 F. I don't know if they're beyond F right now. I don't remember exactly. These are things we can easily inspect for and look for. But if there's a functional performance change that changes, what the potential root cause is. Each one of these could change our direction in terms of trying to figure out what the failure is. Functional performance, in-circuit testing, functional testing. You might be doing some of these types of tests before sending your products out into the field. I know it's not technically production, but what I will tell you is it's still in your factory, right? It still may be a step that's happening in your factory before it goes out the door. So if we can identify, well, we didn't find it on the line, it wasn't a stencil printer issue, and the SPI found it, it's something that happened later in the factory, that's very, very important. Some companies will do environmental testing. The military is a very good example. They do something called ESS testing, environmental stress screening, where every product, 100% of everything you build goes into a humidity chamber, or 100% of everything you build goes into high temperature storage, or something to try to make sure nothing's wrong with the manufacturing process. So all of this potentially could be happening within your factory. Customer rejection. There's a Spanish word. Misspelled? Oh, great. Okay. Anyway, I tried. Okay. And there's misspellings in English too, so it all works out. The customer rejection is more, I was thinking it's not so much the recall, right? Which is, how do you say that? Rechazo? That's a recall, right? It's something in between, like, before it gets to that degree. We already talked about that. But here we're in our own factory, we're within our four walls, and now it's gone out. What happens between here and here? That's not your fault. Transportation, who said that? Nice job. Transportation is going by air, it's going by ship. Is it going by truck down one of these side roads? Topes, I know that word. Right? And under certain scenarios, right, your customer might demand that the truck has air suspension. Right? Why do they do that? Why do you think they do that? Not the obvious answer is, well, because it's less stressful. The real answer is because something failed. 10 years ago, something broke. And someone did failure analysis and determined it was too stressful the way it was being shipped. And from that point forward, whether it makes sense or not, we're shipping bananas. They say put it on an air suspension truck. It has nothing to do with electronics anymore. So you're stuck. You're stuck to find a trucking company that has that option and pay more for it. Some things make sense, some don't. So this, I remember now. Customer rejection is maybe you're sending it to a secondary manufacturer. It's not your SMT process. They're putting it into a medical device. They're putting it into an automotive, a car or something. You don't build the car, but you build the board that goes in the car. So here, this is going to be the manufacturing of the car. The car's not working. It gets returned. So it's still outside of your four walls. Field return is the car works. They send it out to me, and I'm driving it down the road, and then it breaks. So the field return is potentially more dramatic. And it gets more difficult. As you go further and further in the line, it gets more difficult to determine the root cause. Warranty period, if you're lucky. Prior to recall, if you're lucky. Usually it's found by some form of a functional failure. It's not working right. Useful life. I explain this to my students. It's a very sore subject because cell phones have become so expensive. But as a consumer, I have an iPhone. I have a warranty from Apple that within 365 days, 1 year, if it breaks, I can get a new iPhone. If it fails on the 13th month, what happens? I have to pay for it. Apple says, it's not my problem anymore, it's your problem. But will I buy another iPhone again after that? Because I got to go buy another $700,000, $800,000 telephone. I'm not going to do that. I'm going to say, I'm an Android user now, right? Because I paid all this money for this phone. It broke right after the warranty period. So I'm not going to risk again. So companies are designing, there's that term, design for reliability. They're designing their products for the useful life. Same story, but now my phone breaks after 6 years, 7 years. I, as the customer, say, 6 years, that's pretty good, right? Am I going to go buy another iPhone? No, he says no. We have an Android user in the crowd. So, yeah, probably. I'll go buy another. I'm happy with the product. The customer, I'm probably not a good example, but I know nothing about, let's pretend I know nothing about reliability, right? I'm a poet, I'm a musician, right? But even I understand, man, it survived 6 years. That's pretty good. I have no reason to believe that it should be anything different, but I'm going to go buy it again. So we want to understand the useful life of a product and design it to survive that long. If it fails any less than that, 2 years, the company should be concerned because it affects their reputation if it fails before the end of the useful life. Field environment condition. Then we ask ourselves, well, why did it fail early, right? Past the warranty, before a customer expects it to fail, what happened to this phone? Why? Is it one phone? Apple doesn't care. Is it 1,000 phones? Probably a clumsy person, right? Dipped it in some tequila or something. I don't know, right? But if it's 1 million phones, now Apple cares. And unfortunately, it's 3 years later. It's 2 years later. What are they going to do to overcome that problem? Because they've probably been making the same mistake for the last 3 years in production, potentially. Okay. So failure timeline is very important. And one of the first things you should do when doing failure analysis is ask questions to try to identify, I didn't put an arrow, but where is this process occurring? Tracking of date codes, serial numbers, reels of components, right? Are you doing that today? If you have a problem after production, it goes out into the customer's location to be put into a car, and they say, these are bad. We have tombstones or we have non-wets on a BGA or something like that, head and pillows. Can you say, oh, that's from this lot of components we bought from this company? Let's quarantine that lot of components, but we're going to still send you product because we know that we started using a new bag. We cut open a new bag, and this is a new lot of components after this date, after this serial number of your production. So we can quarantine based upon tracking, right? So it's important. So identifying when something happens and having a lot of data as to its scope, for a lack of a better term, saying, this is the serial number. These are the date codes of the circuit boards. These are the date codes of every single component that was used at that timeline. And we're going to take that group and put it to the side, but we're still shipping you product because this is probably associated with a bad component. It's very useful. Okay? Make sense? Okay. Taking this from various different literature sources, this is a very, very famous pie chart. Has anybody seen something like this before? Yeah. So, solder paste manufacturers and printing companies hate this slide because they don't want to be blamed for all the production failures associated with manufacturing. And this is a funny citation because, well, who the hell knows if it's 0.8? It's like significant figures over here, right? But what most people will begrudgingly, they're not happy about it, but they will agree to probably 50%, maybe a little bit more, maybe a little bit less. It has to do with the printing process of your solder paste, ensuring you have perfect quality. And it goes back to the IPC 610 standard, right? Because the paste you put on your board is controlling the shape and the quality of the solder joint when it goes through after it comes out of the reflow oven. BGAs, CSPs, anything that comes with solder on it, we can argue how important the volume of paste is. You want some on there. You need the flux more than the paste. But every other component, leaded devices, gull-wing leaded, J-leaded devices, N-terminated resistors, capacitors, diodes, they rely on this solder paste. And maybe it works, it functions, but then you send it out in the field and you don't pass the IPC 25% wetting requirement and it fails early, right? Just an example. Components, I told you tracking date codes and things. I've done many failure analysis projects where one lot of resistors is contaminated for one reason or another, and it just doesn't solder as well. It produces more tombstones, produces poor wetting, produces all sorts of different things. And what we want to do is we want to pull those components out and don't send those to the customer. Don't send those to the next manufacturing process. Placement, that's your pick and place machine. Again, placement companies will argue. Say, what do you mean 50? We have the most expensive machine on the line, the most heavily engineered. We know every placement is perfect and accurate. If you're placing something small like an 0201 or an 01005, God help you if you have static electricity. Parts are jumping all over the place. The machine put it where you programmed to put it, but then when it let go of the part, it jumped, right? So there's lots of reasons why placement potentially could result in a problem. In certain scenarios, I've heard people blowing ionized air inside the pick and place machine to control static electricity. It's a whole field of robotics, by the way. How do you know the end effector at the tip of my little robot isn't collecting a static electric charge as it moves and touches all sorts of different surfaces and rubs up against things, right? So it's also a field of considerable R&D in the area of robotics. Reflow soldering and cleaning, another 15%. That's two completely different things. Reflow soldering and cleaning maybe contributes to electrical defects. Don't just think about soldering defects. Think about electrical defects. All it takes is a little bit of current to flow between these two little, very close electrical connections, and you have electrical leakage, and things like crystal clocks and things of that speed, that what is controlling the rate and the communications of the entire motherboard is affected. And now parts aren't talking to each other, timing is off, and it's because you have a little bit of contamination on the surface of the board. And not only contamination, but if you didn't reflow it hot enough, you can remain with residues on the surface of the board that can conduct electricity, especially in the presence of humidity. I have no slides on that topic, by the way. If you're interested in that, go find a paper on it. This is one that you don't see as often. Okay, so the previous one was production-related, manufacturing defects. This is, oh, I covered up the source. My bad. I'll have to fix that. Oh, goodness. Sorry, everyone. This is a good time for me to pause. These are environmental factors. Why would something fail out in the field, right? The primary reason that products may fail out in the field is temperature related. It doesn't necessarily have to be temperature of the room, although clearly that has an impact. But my laptop is also a tablet, and when I'm doing presentations like this, and it gets incredibly hot, right? This product gets, oh man, it is hot right now. And this is blowing hot air right on my laptop too, right? So heat is not your friend in electronics. Electrical engineers will understand heat is not your friend because you get your processors run slower. That's why kids who like to design their own gaming computers use liquid cooling, right? They can run at higher clock speeds if you're colder. That's one thing. That's functional electrical performance. But heat is also not your friend when it comes to materials. Materials expand and contract, and you heat them, they can become put under stress, right? A very simple example, although no one has these anymore, is a thermostat. If you were a kid and you ever tore apart a thermostat, there was a little metal coil in there, and that would change its resistance from heating and cooling because there was two different metals on it. It's called a bimetallic strip, and they would expand and contract at different rates and change the resistivity of that coil. Vibration, humidity, sand and dust, brine, which is salt water, altitude, thermal shock, are all causes for why something might fail out in the field. We talked about vibration in shipping your products from one location to the other. So let's talk quickly about defects. Defects that are common in production are opens, electrical opens, right, where you don't have a soldered interconnection. Shorts, where you have electrical contact between two adjacent terminations. These are very easy to identify, right, because they're visible. This is a leaded device. I could take a nice picture of it. But what you can't do is do that as easily on a BGA. If you have a device where all the terminations, all the electrical connections are underneath the part, you need something else. You can't find it so easily. Functional test failures, here's an eye chart, right? That becomes more difficult. It's a different type of defect, and we don't know what the cause is. It's not necessarily an open, it's not necessarily a short, it's something else that's causing an electrical performance issue. And we could make a long list of reasons here, but I don't want to get into that today. So if it's a short, how do you identify and evaluate them? You know, identify is easy. What's the failure mode? Oh, okay, it's not connected or whatever. But then we want to evaluate, is it repairable? Is it not repairable? What's the cause of it, right? We want to go down a little bit further when it comes to a short. Here's a short you may have never seen before. Um, Anybody know what this one's called? It's an acronym. What? It's not a whisker because this is occurring inside the circuit board. So what's that? ECM. Electro. Yeah. Yeah. Yes. You're getting closer. Our industry has a specific term for this. Yeah, that's another one. But even more specific, there's even a standard on it. I don't know if there's a standard. There's a test methodology to try to test for this if you are evaluating a new board house. It's called a conductive anodic filament. CAF is the acronym. And what's happening here is between these two drilled holes, there's a separation, a delamination, and one is a ground and the other one 12 volts, let's say, 5 volts. There's an electrical difference between there you get your anodic term, right? And you're basically plating inside your circuit board a little strip of copper, all right? It's conductive because there's a fluid in there. The root cause is more complicated, right? But this happened, and the way the customer found it was every 20 minutes, the computer would reboot, right? And they start it up again, 20 minutes later, reboot again. And I said, wait 19 minutes, shut it off and send it to me. And we were able, with the help of some electrical engineers, and I'll talk about this later in the destructive analysis, and we were able to isolate these two routing paths through the board as being shorted when they were not supposed to be shorted. Very low resistance. So then it was a needle in a haystack scenario to try to figure out where this possibly could be. And I'll be the first to admit, I took these pictures. This is not from a source. I was incredibly lucky to ever find the thing in the first place, right? And if you had a problem like this on your product, you may never figure it out, right? But it's possible. It takes a lot of effort, takes a lot of time. Time is money, right? I will tell you, this particular failure, one failure, could have cost the company millions, tens of millions of dollars. So they spent a lot of money trying to figure out exactly what was going on here. It took me months to figure this out. Defect identification. Okay, so we're moving on, okay? The only thing I want to say is I showed you an example of a short. Opens, shorts, simple things, right? It can be much, much more complicated, but I wanted to provide this audience with a list of terms for various different types of defect identification. Think of this list I'm about to show you as your toolkit. These are all tools that can be used to try to explain or identify a failure, one different from another. So there's a lot of non-destructive methodologies out there at your disposal in a manufacturing environment. Some are more common, others are expensive. Automated optical inspection, AOI, you're probably familiar with that. That's a methodology for you in production to keep an eye on things. I should have included here, and there's probably some very offended suppliers, SPI too, right? It's non-destructive. Infrared inspection, we're looking for heat, right? We can actually put an infrared camera on the surface of your board, turn it on, and look for hot spots. It's something that can be done. X-ray radiography, X-ray laminography, and X-ray computer topography, or CT tomography, I'm sorry. All sorts of X-ray techniques. This costs, $50,000 to $80,000. This one costs $100,000 to $200,000, and nowadays this one $250,000 to over $1 million, right? Very expensive. It gets more and more complicated. Prices are coming down, but and I have examples of what those look like. Ultrasonic imaging, people are familiar with looking at human organs using ultrasound. Same medical technology, but they use a different wavelength. We can look inside of your circuit board using sound and identify voids, delaminations, defects in things that You can take the board out. It's done in deionized water. You can dry it, wash it if you want another time through the wash machine, and it's non-destructive. But you can look at things using ultrasonic imaging. I don't have a slide on that today for time. Someone's got to keep me honest here. Oh man, we're running a little slow. But the thing is that ultrasonic is like light things like voids. X-ray is heavy things like solder, right? So they're used for different reasons. Optical techniques, moire techniques, and alphabet soup of analytical tools I'm not going to get into. But they are useful. Destructive analysis, you probably know about cross-sectioning, a technique called dye penetration, electrical isolation, cutting traces, breaking the board, trying to isolate. I showed you the previous failure where we were able to identify two routing paths as being shorted. The only way to really figure that out is cut traces, because there's all sorts of connections through components to other areas. Physical testing, vibration, bending, shear testing, chemical testing, decapsulation can be done to destroy the board in part or the assembly, but then know exactly how you broke it and then or destroy it to prove one way or the other where the problem comes from. So shorts like non-destructive, we have X-ray, we have microscope inspection. These are non-destructive ways of looking at your board, and you can still send products to a customer. Good luck finding a short here. Can you see it? No. I'll tell you, this is the same board I showed you the flat section and cross section from. So in here somewhere, I forget which ones it was. It's like these two or those two are the ones I eventually found the shorted. This is before cross-sectioning, yeah. We were hopeful we'd be able to find something. It was in our toolbox, so we used it. And later, when we knew what the problem was, we noticed that the holes were not of one diameter. The wall kind of got gray and fuzzy, and then it got well defined again. And I didn't mention it earlier. The root cause for that calf was the drill was too dull and too fast. They were drilling holes in the board. Rather than cutting the material, they were punching. Yeah, and they fractured it. They broke the glass, and when the holes were really close to one another, it would delaminate enough to create an air gap, and then it would fail. And the evidence of that was even visible in X-ray, but we didn't have enough information to go back to the customer and say, this is conclusively your problem. We had to do the destructive analysis. There it is again. I knew I was going to repeat myself. So in order to do that, you have to do destructive analysis. We saw something weird, but we didn't have enough information to convince the customer that's what the problem was. And it wasn't even my customer. The customer was the OEM. It was the owner of the product. We had to convince the board supplier that they were doing something wrong. Because again, there were tens of millions of dollars worth of liability in this particular type of failure from one board. When you evaluate, you identify a short. But if you do it properly, was also in my abstract of the presentation today, if you do a proper evaluation, it can lead to root cause, it can lead to the failure mechanism, and it can lead to the physics of failure. It's probably in the wrong order. Failure mechanism, physics of failure, those are sort of the same term said in a different way. And then ultimately, if you know these two, hopefully, not guaranteed, because there's so many things that can go wrong, but hopefully you get to some level of root cause. So if you do all this, you can maybe get the correct identification. In order to do these things, very often you need a very close relationship with your suppliers, right? You need to really understand, you need to be able to have trust with your suppliers to be able to say, guys, you gave me a board. It looks strange. I'm having these, something's wrong. You know, what could have happened that day? Did you use I had one failure analysis had to do with expired prepreg. How the heck would you know that your prepreg, I don't know if any of you know what prepreg is, that's the material that's used for gluing the layers of the board together, was expired. You'd never know. You'd have absolutely no clue. Knowledge of the process, you need to have really, really, really deep knowledge of printing, placement, reflow to be able to eliminate things, and then material behavior helps too. Root cause is not process control, but all these things you may have learned in industrial engineering, lean manufacturing, Six Sigma, SIPOC, DMAIC, FMEA, PFMEAs, Ishikawa diagrams or fishbone diagrams, they're also part of your toolkit. We talked about non-destructive and destructive analysis, but these are also ways for us to segregate the process, the manufacturing on different dates and different ways to try to better understand what actually happened on that particular board on that particular day. Again, this is not a lesson on any of this stuff. I'm not an industrial engineer. I'm a material scientist. But I've learned these can be very powerful tools, and if you're interested, you can learn more about them. Here is a fishbone diagram, intermittent failures in electronic assemblies. Failure analysis, if you leave here today, and I'm going to go maybe right up to an hour, if you leave here today with anything, failure analysis often is more a process of elimination than saying, oh, this is your problem. Go fix that, and everything is fine. Because we have such a complicated manufacturing process. What happened? Ah, for goodness sakes. Sorry. You know, if you've ever done one of these before, you know, there's connectors, there's printed circuit boards, there's component PCB interconnections, they're the components themselves, and those are the main categories. But then within connectors, I can't even read it. Plating, environment, corrosion, wiring, wear out, aging, damaged leads, printed circuit boards. The major ones are whiskers, warpage, via cracking, electrochemical migration. Ooh, there's that term. Someone used it. And then thickness, quality, plating. If I can determine your board's fine, gone. This whole quadrant is gone, right? If we can look at your component PCB interconnects and determine, well, you're printing the right amount of paste, solder looks great, flux residues look good, I don't think you're doing anything wrong with your SMT process, gone, right? So it's more about eliminating and using your toolbox to point as evidence that we were able to eliminate this. Now it's down to the components. Oh, okay. Well, now we use our SEM, we use our other tools, that acronym list I didn't get into, to figure out what's happening with the components. Is there a organic material on it? We had years and years ago, this is not even my project, my boss had it, they were getting boards from China in the 80s, and they were using shoe polish to polish the boards before they sent it to the customer. Right, so there's a layer of paraffin wax on the boards. It doesn't solder. You don't know it's there, right? But you need to use organic chemistry to figure out, oh, that's paraffin. Paraffin is a form of wax. Case closed, done, send it back. We know exactly what happened, right? There's no way to argue that point. All right, anyway. Non-destructive analysis, AOI. I think I'm not going to spend any time on that because I'm a little bit late. You all know about AOI. Where is it? AOI can be put in multiple locations in your manufacturing process. If it detects a failure here, we can eliminate, in my fishbone diagram, a whole bunch of potential root causes. If I find it here, good luck, right? But here, it's not a soldering issue. It's not a reflow issue. It's not a contamination issue, potentially. It's a electrostatic issue in my pick and place machine. It's a printing defect. It's something other than a soldering issue. I'm not going to get into that. You're welcome to read this afterwards. I think this is more of a lesson on AOI than anything else. X-ray radiography. This is the X-ray you get if you go quickly to a doctor's office. They may even have that in a regional doctor's office. And it's just taking two-dimensional images. Oh, there's a missing wire bond. This is a really dumb X-ray because we could look at it under a microscope, but no solder joint. Here, this one's maybe not as obvious because X-rays have a parallax issue, like near the edges. It doesn't look the same as if you look it straight down the middle. But if this is one that's straight down the middle, why is that drilled hole not in the center of the pad, right? Non-destructive, but I have concluded without a shadow of a doubt that the drill was not in the right location. X-ray laminography, it can be done rather quickly. There are even tools you can buy that are in line. And it creates layers of images, right? And the concept here is that things that are closer to the source of the X-rays move at a slower rate than things that are further away. And the computer picks out those pixels that are moving relative to the other ones, and it creates separate images for anything that has a certain velocity. It's a super simplification of what's going on, but you can then look at your printed circuit board assembly at different depths, and it's still images, and it can be done rather quickly in production. 100% inspection can be used. Some people, there's articles about this on the knowledge base, have used this to determine head and pillow. Anybody know what head and pillow is? Yeah, head on pillow, head in pillow. I don't know. Everybody calls it something different. I have a picture of it, but you're absolutely right. So this tool can be used if you're looking at the right depth to say the bottom of my BGA solder ball is supposed to look like a sphere, not like two spheres, right? So you can see different defects when you laminate it in X-ray. Non-destructive, again. CT X-ray, you're creating a three-dimensional CAD drawing right, of a location on a board. And some of these tools have become incredible, where we can actually see the phase separation of the lead and the tin, because lead is such a heavy element. So really unbelievable. I know I've had a customer who had one of these. They stopped doing cross-sectioning for certain types of failure modes. Why is X-ray dangerous, if I want to use that term? Because it can't see everything. Right? If you have a solder ball that's not touching the board, if you have a solder ball that looks like that, is deformed, if you have a solder ball that's slightly bridged, I know that's hard to tell, that picture is quite bad. When you use a high energy beam of electrons, it blows through all that stuff, you can't tell. Looks like a perfect circle. So, X-ray is great, but it doesn't mean you don't have a failure. It means you have to maybe go look a different way and see it in a different methodology, like just optically. Because all of these pictures potentially look like that. Perfect. Right? But you don't know, because all these other defects could be occurring that aren't visible by X-ray. Removal of silver tarnish. This one doesn't really fit the presentation, but I like showing it. Right? If you have a silver surface finish, the pink pearl eraser, you find these in manufacturing all the time. There's the manufacturer and the part number. It's really effective at removing tarnish. A lot of companies use this to repair fiducials that aren't working. Anybody do that? No? It works. It's not good, but it works. You don't have to use it, but is it a methodology for overcoming fiducial alignment issues? And some soldering. This is not something you want to do on every single board. Right? Prototyping, something like that's okay, but not in production necessarily. We have to ask ourselves, why the hell do we have tarnished silver surfaces? Destructive, is it okay if I go a little bit longer? Okay. All right. The suppliers will be very angry with us, but. Dye penetration. Anybody done dye penetration? Dye and pry? Yeah. Here's a very generic methodology. You submerge your circuit board in dye. It's I may have taken the slide out. It's a steel layout fluid. Machinists use it. Dye chem, blah, blah, blah. It's this very specific type of dye. Why do we use it? Very low viscosity, deep, deep dark red. So when it gets into very thin areas, it can be hard to see it. Some methodologies also include a UV illuminating material, but this dye stuff I've used for years. You put it into a vacuum, not too high a vacuum because this will begin to boil. You don't want that. You dry it out for 30 to 60 minutes at 100 to 125 degrees Celsius, not 100,000 degrees Celsius. I forgot the little dash in there. But we want to dry it out, right? And then we remove the component mechanically. There are different ways of doing it. This is not necessarily the best way to do it, but you want to remove it without overly damaging your component. So you're just literally popping the BGA off the surface. And what you're looking for is the presence of dye. I had a colleague at Universal Instruments. He would say this really stupid phrase: you have to have the eye for the dye. You need to be able to actually see it. And what are you looking for are cracks anywhere. This example is showing a crack underneath the copper pad in the laminate material of the circuit board. Here's another one, but this one is now happening on the component side, on the top side. So, different failure mechanisms, different sides. Component side versus board side, I'm eliminating portions of my fishbone diagram. I'm trying to figure out exactly where and when these things are occurring. Unfortunately, this is kind of hard to see under this light, but we have a cracked intermetallic fracture and we have a pad rupture. We have two different failure modes. So why is that happening, right? It's not inherently a brittle intermetallic if not only is the intermetallic breaking, but you're also tearing pads out of the board. So when I saw that, this is in addition to dye penetration. Dye penetration is destructive anyway, so I may as well cross-section a few anyway. I said, man, someone threw this board across the room. It was some really excessive amount of stress that isn't indicative of what the product will actually see in the normal production environment. I wanted to say something else about this, and it escapes me at the moment. But electrical isolation, it's hard to see, but there was a trace here that was cut and resoldered, right? An electrical engineer, a good test tech, can help you narrow your search for where the failure is occurring, the functional failure is occurring. It's destructive. It's not something you'd want to send to the customer, but it helps you identify locations on your circuit board where you want to spend most of your time looking for the failure. Some other real quick examples. I'm almost done. If you have any chip resistors like this, the way they function is a bed of ceramic, and they put a conductive film on the surface, a glaze, and they fire it just like your pottery that you might have at home. And the end terminations very often have silver in them. Underneath the solderable surface, there's a layer of silver on the less expensive parts. And there's a gap. There can be a gap between the protective layer and the end termination. And if you expose these parts to diesel fumes, rotting food, in some cases charging batteries, you get a hydrogen sulfide gas in the air. It's not dangerous to humans, but it's got sulfur in it. And you can begin, the sulfur will attack the silver and form silver sulfide. It can look like this. Little black stuff at the end termination of your resistor, and under an SCM you have these needles of silver and sulfur with an EDX, with an energy dispersive X-ray system. You can determine that there's sulfur in there. It's not a slam dunk, but I know what's going on. I know the mechanism. I know the physics of failure, to use that term. But why? This particular customer, it was happening in one corner of the board, but not another. When we found out in the chassis, it was like a desktop computer. The ones that were failing were right next to the fan. So it was blowing this hydrogen sulfide gas at a higher rate near these parts, and they all were failing, but these failed first. Okay? It can happen under conformal coating. Certain conformal coatings are not protective of hydrogen sulfide gas. In fact, silicone, you may not know this, it absorbs hydrogen sulfide. So the failure mechanism can actually be accelerated if you coat your boards with silicone encapsulation materials. And then instead of a nice needle, you get, because it's encapsulated, you get little spherical balls. But the end result is the same. You get an electrical open. So if this breaks, the resistive layer is no longer attached to the termination, and your resistance goes up first, and then eventually it's an electrical open. Package warpage, producing something like a head and pillow. There's a picture of it. There's a picture of Shadow Moray as a technique. Oh, I don't think I had that on my non-destructive analysis. This is non-destructive, actually. We did an analysis of on a package-on-package component, how much warpage there was on the top package versus how much warpage was on the bottom. The tricky part here was it didn't violate standards. It didn't warp all that much. But because the warpage was different on the top and the bottom, it was like taking a Pringles potato chip, you guys know what that is, and churning it upside down and putting it back into the container. If it's not shaped in the same direction, the gaps can be much, much larger and not comply. Delamination or mesoling. Look at all these little bubbles that are occurring on the surface of the board. Some additional defects. Delaminations could be more difficult to see, discolorations. There's sort of an amoeba, an unusual shape underneath this ground plane. Some mask lifting. When you cross-section it, now this is after 9 reflows at 260 degrees, we saw all sorts of breaking of the dielectric material inside the board and lifting. What's unique here, if you're a board manufacturing expert, is it was happening on every odd layer. So this was a prepreg related issue, not a core related issue. Cross-sectioning, right? Cross-sectioning is the tool. Knowing the manufacturing process of circuit boards is necessary to be able to eliminate one area of the fishbone diagram. Here we eliminated cores. We recognized that the problem was related to prepreg. Another example. This is another delamination, but now instead of at the core, it's an adhesion issue between the prepreg and the copper layer. Maybe they didn't oxidize it properly, right? They didn't do the adhesion promotion that is required on inner layers, cores, before doing a prepreg lamination process. So, I'm getting into some of the details, but this is like cross-sectioning is the tool, and then you have to have that knowledge in order to get to the root cause. Here's a crazy one. Knee fractures in the plated through hole. Does anybody know what these lines are? This is copper. This is your nickel. Very thin layer of gold. What's nickel gold called? ENIG. Electrolysis nickel immersion gold. This is your ENIG layer. So everything else in here is copper. Do you recognize that this looks different than this stuff over here? What's this? And not only that, let me point out a little peninsula here. Anybody do machining, drilling? This is called, in English, called a burr. You don't deburr, you punch or you drill through metal, and you get a little piece of metal at the edge of where you drilled. That's been drilled goes through a deburring operation. They didn't deburr. That's problem number one. This is your copper foil from your core, or if it's a foil lamination process, it's the rolled annealed copper that gets put on the top. And then they plate copper on top of it using a two-step process. One is electrolysis, and another one is electrolytic plating. Electrolysis plating gives you the electrical path inside the hole you just drilled. Electrolytic plating builds your copper thickness inside the hole. The whole point of this is to get the hole to be the proper thickness copper. I've told you enough in about 10 seconds. What's the problem with this? It should be done once. Electrolys, electrolytic. How many, did they do it once or more than once? What's that? Several times. Every little line here is another electrolytic step. They plated the first time and got that much copper, this much. Oh, it's not enough. Put it back in the bath. Do it again. Do it again. Do it again. Forget it. Let's leave it overnight. We'll come back tomorrow. And finally, they got enough copper to pass something. I don't know, some electrical test, some burn-in test. And they shipped it off to the customer. But it made a weak interconnect there because of the burr and plus everything else that they were doing wrong, and resulted in that to crack in that location. Caused an electrical open. The failure mode is open, but there's so many ways you can get it open. More opens. Barrel cracking, foil cracking, all these things can happen as well. Cross sections are the tools, but if we see a crack at a different location, the root cause is a different reason. I eliminate an area of the fishbone diagram. Champagne voids, you can type that in the search engine and find all sorts of cool stuff. It has to do with the silver plating process on the copper and causing these little tiny voids. Okay, I've gone far enough. Thank you very much. I want to thank the chapter, and I want to thank all the universities I visited this week as well.
Sabemos que esta presentación es muy extensa, pero muy importante. Lo que se vio ahorita aquí se grabó para ti, pero nosotros tenemos la presentación y vamos a buscar la manera de hacerse llegar, porque ahorita por la velocidad podemos conseguir todo.
Yeah. So if you search failure analysis or even a specific failure mode in the knowledge base, I guarantee you'll get a hit or two. We have over 6,000 papers starting from the 80s. I think maybe not 80s. I'm exaggerating. Probably the 90s sometime. From multiple, as an organization, we have 3 conferences a year. We require the speakers to write a paper. Thank God you didn't require me to write a paper today. But with 3 of our conferences, there's a wafer level, there's the SMTAI, and Tanya is going to remind me what the other one is. But there's another one. And all those papers end up in the knowledge base. I think there's one in Europe. My boss said I didn't charge enough. It got to the point where we wouldn't do anything if it wasn't worth $5,000. Okay, so that was sort of U.S., right? So that's my old lab. I don't know what they're doing now. Don't ask me, right? But you can get a lot of information with $5,000, right? You're basically buying the access to the tool and a skilled operator for a number of hours of their time. And also, we would also write a final report, like a report on everything that we find. And you can find lots of labs that'll do that. And there are labs that are very good at identifying the failure mode, but then they can't necessarily help you with root cause. They don't know enough about the process to be able to say, well, this happened because blah, 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 blah. They won't ask you any questions. Just send us the boards, we'll cross-section them. But you have a good failure analysis lab where you're on the phone with them for 2 hours and they're just bombarding you with questions, more questions, more questions, more questions, because they're eliminating the branches of that fishbone diagram. Good question. Don't hold me to that number. I've done projects that were over $100,000 too. So it can be $5,000 to $100,000, right? Yes, question in the back? Not by the time, yeah, I know where you're going. Not by the time I got them. Because you have to understand, I'm biased. People didn't come to me until we got all these weird ones, right? one company called them the bones pile. Like there's an area in your factory where people put things that they can't figure out, right? So when that becomes painful enough, then I would be contacted. If it's a paste related issue, this one of the earlier bullets I said you have to have very good relationships with your suppliers. I've had many conversations with paste suppliers. They walk into the factory or they're on the phone with you. It costs you nothing, by the way. And they say, when's the last time you changed your stencil? Right? What is your storage methodology for your solder paste? So they're doing what I just said. They're eliminating segments of the fishbone diagram, but they're asking, like, you know, it's like when you call Microsoft and they say, did you reboot your computer? Right? It's like things that are obvious, but they're going to ask you to eliminate a lot of possibilities. And usually, if it's a paste printing issue, it's solvable, quote unquote, right? Unless there's a design related concern. And then I have gotten involved in those, right? I can't say I've never had a paste related failure analysis, but it's the more complicated ones that then require me to write a report that goes back to the designers or to your customer that said, please build this thing, and say, man, we tried. Here's a report that says it's your problem. You know, so it's not 63. It's the stuff that I've done. I'll tell you, for me, 50% of them are board related, right? Hidden things inside the board that are causing electrical functional failures. Bare board, board supplier problem. And not to the fault of the board supplier necessarily. This could be a challenging design. It could be just a bad day, whatever. You know, that drilling issue, that board house is still the supplier for that company. They just didn't realize they weren't retipping properly and doing a couple of other things. The backing material you're supposed to put in too, they didn't do that. They stack multiple boards together too when doing drilling. There's all sorts of crazy stuff that they do to save money and time. Yes. Mm-hmm. Yes. Even 2D X-ray can. Because X-ray is the non-destructive way. Dye penetration is the other that allows me to look over a large area. Sometimes if a customer gives me no information, they say, this doesn't work. Can you go find the problem? I need to do some brute force methodology to say, well, does this board look normal under X-ray? I'm going to look at the whole design, everything, the whole PCBA, everything. And then, or I'll do a dye penetration of all the BGAs. It's destructive, but I'm going to verify that all 10,000 solder joints underneath the BGAs all look like they've been soldered correctly. Then, if I find something strange, then I hope to have another failure, another board, that I can do a cross-section analysis on, because then it's guiding me in the direction of determining root cause. So yes, I will use multiple techniques on any given failure analysis project, and X-ray can be very valuable. Knowing the limitations though, right? I'm not going to eliminate shorting or bridging just because I don't see it under the X-ray. It could still be there, but it might just be a very subtle bridge. We didn't get into, what's the name of the term? If you're underfilling your BGAs or encapsulating them, if there's delaminations, you can get like a creep behavior that has nothing to do with electromigration. Solder will just work its way into holes. It's very strange from hydrostatic pressure. Yep. Come on, challenge me. I want to get a good one. Yeah. Mm-hmm. At the university. Yeah. Yeah. So let me repeat the question for the people in the back. Um, some manufacturers are having difficulty proving to their customers that they maybe have a design issue. How do you even start that, right? You tell them there's a design issue, but they don't believe you or whatever. So the question really is, how do you here in Juarez start a group of individuals that have those types of skills? I think you have the skills, maybe even in this room. Someone worked for a company that did board fabrication, right? The raw board fabrication. You have somebody who worked for a solder paste supplier. You have somebody who worked years in the SMT manufacturing space. You have somebody at a university that has EBSD and has TGA and FTIR and ATR and all these other analytical tools. So start a company. I mean, it's not a joke. You need to collect a few of these people, and you're not going to get rich doing it, by the way, right? It's not a scalable. It's not scalable because we were making $5,000 a pop, and these are expensive employees, right? With PhDs or whatever else. They don't have to have PhDs, but they have many years of experience, so they may as well have a PhD, right? So. So it's hard. It's not easy. But I think it does start a little bit from the universities, right? Because there are certain tools and skills. You have the presentation now, right? Go find out who has these tools in your vicinity. Make a list. Eduardo's probably very good at that, right? Find out who and where are all these, what are the assets that exist in your 5 universities that I saw yesterday? Make a list and say, okay. Martin said, try this test. Let's go out there and try it, kind of a thing. One of the labs I went to in one of the universities, SMT lab, I said, where's the sink? Sink? What the hell do we need a sink in an SMT lab? Who's doing the cross sections? It's a university. Where's the polishing unit? Where's the epoxy? And you don't want to put it next to the SEM. It's dirty. You're going to flood the room because some student's going to pour the epoxy down the drain, right? And then it's going to solidify in there. So you need a space for that, to do some of these simple things that don't exist. And I was going to give that list to Eduardo as well. I know we went too long. Thank you very much, everybody.
Buenas tardes, pues vamos a dar inicio con la rifa de la Smart TV. Entonces, vamos a hacer la misma dinámica que se hizo más temprano. Vamos a sacar 2 boletos, esos serían los no ganadores, y el tercero sería el que es el ganador. Así que preparen ahí sus tickets, sus números, y vamos a sacar el primero. El primero es la terminación 09. Terminación 0. ¿Qué pasó, doctor? Sí, otra vez. Sí, no. El segundo ticket es la terminación 073. 073. Cerca. Bueno, y el tercer número es la terminación. Felicidades al que tenga la terminación 059. 059. 059. A las 2. 059. A las 3 sacamos. Ah, a ver. Ingeniero Luis. Nomás Luis. Muchas felicidades, Luis.
Gracias. Gracias por acompañarnos, jóvenes.